All right, going into our last lesson over logs, we're going to look at how to solve exponential and log equations. So starting out, we're going to look at your exponential equations, and there's two ways you can kind of look at those. You can try to get your bases to match. So try to get this number and this number to be the same. And that's kind of how we looked at our laws of logs. Can we rewrite the numbers so that they match so that we can look at just your exponents? This will mean that your two exponents will then be equal so long as these are equal. All right, if you can't make the bases match, then you're going to have to switch to log form or use logs to bring down your exponents. So let's look at a couple examples here. If we have 5 to the 2x minus 9 equals 125, we can use logs here, but 125 can be rewritten to match the 5. So if we can do that, then that makes this problem a little bit easier. And so we're going to rewrite 125 as 5 to the third. As soon as you get these two numbers to be the same, then that automatically implies that the exponents are also the same. And so 2x minus 9 is equal to 3. And then from here, you can just use regular linear algebra to solve. So we add the 9 over and then divide by 2. And so x equals 6. You can always go back to your original problem, plug that in and double check. But 6 times 2 is 12, minus 9 is 3, and 5 cubed is 125. So we're good there. Same thing here. You could go ahead and try that on your own if you would like. Okay. When you have an exponent in that power already, when you change that 16 to be your same base, then you're just going to apply your power rule. All right, so whatever exponent you put here will multiply times this exponent here. If your exponent is not isolated, so as in this case where that x minus 2 is only on the 2, all right, there's no way to get 99 and 2 to be the same, but we can divide by 3 first to see if we can then get them to be the same. So this equals 33. So there's still no way to rewrite 33 as a power of 2, right? So when this happens and we get stuck and we can't get these to match in any way, that's where we need to convert to log. So log base 2 of 33 is equal to x minus 2. Adding your 2 over, you get log base 2 of 33 plus 2 equals x. This is your exact answer here. We can't do anything else without using our calculator for that. Okay, so in my calculator, I go to math, log base. If you don't have this option, you will have to use your change the base formula. 2 of 33. Leave my parentheses and then add 2. Otherwise, it's going to be log base 2 of 35 equals. And so that's approximately 7.044. 4 decimal places, sorry. 044. 4 if I round that 9 up. Okay. So approximately 7.0444. Okay. When it says exact solutions, it's talking about this line right here. So we don't type it into our calculator until we have our variable isolated. And that's the best way to approach that. For ones, again, that don't have your exponent term isolated, you want to do that first. And so here we are going to subtract the 4. If there's no way to get the bases to match, that's when you convert then to a log. So log base 3 of 4 equals 5x. If you don't have a log base in your calculator, then use your change of base formula, log of 4 divided by log of 3, to solve that. But here to isolate the x, I'm going to divide by 5. And so I have log base 3 of 4 divided by 5 is equal to x. This is your exact answer. In a graphing calculator, again, if you don't have, or you just don't want to go into math, you could take log of 4 divided by, in my parentheses here, divided by log of 3. And then we're going to divide all of that by 5. All right, and you'll see if you do math and then log base. Goodness gracious. Here we go. Sorry. Can't get my button. Push the right buttons here. Log base. And we have log base 3 of 4. And then we divide that. And then we divide that by 5. You get that same answer. So 0.2524. 2524. So x is approximately 0.2524. All right. For trinomials, we're going to approach them from a factoring standpoint like we always have. And so we have e to the 2x minus e to the x minus 6. We're just looking for, this is no different than something squared. So we're looking for what multiplies to -6 and adds to -1. So we get e to the x minus, let's see, 3, and e to the x plus 2. All right, x times x is 2x, and then x plus x gives us the x in the middle, equals 0. So both of these need solved separately. So we start out looking at e to the x minus 3 equals 0, which means that e to the x equals 3. This, because our variables in our exponent position, needs converted to a log. So the natural log of 3, log base e is natural log, is equal to x. That's your exact answer, your approximate answer. You're just going to take the natural log of 3, and you get 1.0986. So x is approximately 1.0986. We're going to do the same thing with the second one here. We're going to have e to the x equals -2. And so the natural log of -2 equals x. And you'll see here that you'll get an error. And this is because we can't take the log of a negative number. And so this one doesn't exist. And so this is our only answer. Okay, so anytime you do a factoring problem, if that ends up negative, it's an extraneous solution, and you can just move on from there. All right, if you're looking at your log equations, you want to give exact answers unless you're asked for a decimal. So you can make it look like the log of a number is equal to another number, and then we can change to exponential form and solve. Or we can get two logs equal to each other to where we can just take whatever we're taking the logs of and set them equal. So same as your exponentials for that. All right, you must check all solutions to log equations because we have those instances where you can have your extraneous solutions. So make sure you're always looking for extraneous solutions. Make sure your base is positive and you're taking the log of something positive when you're plugging that in. Okay, so we're going to solve these and round to the nearest thousandth. We have the natural log of 2 plus x is equal to 1. My x is trapped behind my log, and so the first thing that I do is convert this. And remember, natural log is log base e. So this is e to the 1 equals 2 plus x. All right, solving this for x, I have x is equal to e to the first minus 2. This I have to go in my calculator and do. You have an e button right here if you want to put the exponent, or right above the divide sign if you don't need an exponent. E to the 1 is just e. So e minus 2 is approximately 0.71828. It's the nearest thousandth, which is 3 out. That 2 is going to round down and keep that 8 at 8. So 0.728. If I have log base x of 18 equals 2, all right, I need to remove my base here. So I move this, x squared is equal to 18. And so I take the square root, and I get x equals typically plus or minus the square root of 18. But because the x originally started in your base position here, the negative case is going to be what's called an extraneous solution, and so that one is ruled out. And so when I simplify, that's 9 and 2, then I get x is equal to positive 3 root 2, which is approximately, if you take the square root of 18 in your calculator, 4.23, excuse me, 4.243 if you're rounding to the nearest thousandth as stated. All right, so we get rid of that negative case there. And you don't really need to simplify your radical here. We could just go from there to there. If you have two logs equal to each other, then we can, as long as the base is the same, ignore the logs altogether. All right, if the log is equal to another log, that means whatever you're taking the log of equals whatever you're taking the log of. And so I'm going to move these to the left here and rewrite this equation as x squared plus 2x minus 24 equals 0. And then I'm going to see if this will factor and solve. This breaks down into 6 and 4, so x plus 6, x minus 4. And so x is equal to negative 6 or positive 4. Now going back to our original equation, we can't take the log of a negative number. All right, we have to make sure we're taking the log of something positive. If I plug negative 6 in here, it becomes positive 36, but then I'm subtracting and it's negative. Also, if I plug negative 6 in here, this is negative 12. So negative 6 is an extraneous solution. And so 4 is the only answer. This is extraneous. All right, so just be aware of that. Okay, giving exact solutions, same thing. We're going to convert from a log to an exponent when we need to. Remember that if you don't see the base, it's a base 10. So this would be base 10 of x squared equals 2. So this is 10 squared equals x squared when we convert it. My bases, because my exponents match, my bases also need to match. And so x equals 10. All right, there's a longer way to do that. You could actually square that out, get it set to 0, factor and solve. If you do it the long way, you're going to end up with negative 10 as well, which is an extraneous solution. All right, or you could square that out, square root both sides, same thing. You'll get the plus or minus, minus gets thrown out. If you have a log on both sides of your equation and there's no way to isolate one, oops, sorry. All right, so there's no way to get this to where it's log equals a log, because if I move the 4 over, then it stays the same. So here's where yesterday's lesson 2 comes in, where we can get all the logs to one side and then rewrite this as multiple logs down to a single log. And so I'm going to move my 3 to the exponent position here and rewrite that as x to the third. And then I'm going to subtract my log x cubed over to the other side. And so this gets rewritten as log of x to the fifth minus the log of x to the third is equal to 4. Well, subtraction converts using your property into a division problem, and this gets rewritten as the log of x to the fifth over x to the third is equal to 4. X to the fifth over x to the third will simplify into log of x squared equals 4. And now I can convert it. And so remember, this is a base 10. 10 to the fourth power is equal to x to the second power. And so this is just 1,000 equals x squared. If I take this, or excuse me, 10,000, I need 4 zeros. If I take the square root of both sides, I don't need the negative root because I can't have a negative x. And so x equals 100. Okay, if you put the plus or minus, then you should see that the minus is extraneous and rule it out. Okay. So same idea here. Anytime we have more than just 2 logs, we can't cancel these out. And so to get it to a point where we can cancel the logs, then we need both sides to just have a single log. And so we can rewrite this as log base 7 of 10 over x minus 3. All right. Another way to do that is to subtract everything to one side and then rewrite it as, so we would subtract this and add this and then rewrite it as a single log. Okay, get it set to 0. That's also fine. But if you go this approach, these logs now cancel, and so we know that x is equal to 10 over x minus 3. Multiplying both sides by x minus 3 to get rid of the denominator, I end up with x squared minus 3x equals 10. And so x squared minus 3x minus 10 equals 0. This factors into minus 5 and plus 2. X cannot be a negative number. It also can't be 3, but that's not an issue here. And so x equals 5 will be my only solution because negative 2 won't work. All right, so any questions on that, just let me know. Moving into your word problems. And so exponential growth and exponential decay are modeled with specific formulas. And so a lot of times you can use just your population growth formula. You'll see a lot of similarities with these and those. But exponential growth, if you're doubling your population, you can use this. The 2 is because we're doubling. If we were tripling, that could just change for a 3. Or we have a formula for population growth that might give us a percentage, but not like how much it's going each time. All right. Anytime you see a sub-zero on anything, it's your initial amount. So in this particular case, it's the initial size of the population. If we're talking about the population of something. A is your doubling time. How long does it take to double the amount? Your labels on A and T must match. So either they're both minutes, they're both hours, they're both seconds, whatever, they have to match. If you're not necessarily doubling, but you're still growing in some way, N sub 0 is still the initial size of the population. R is going to be your relative rate of growth. As a decimal. So percentages should always get converted to decimals. T is still just time. All right, so if you need to know T is time, you need to write that out. All right, so again, M sub 0 is initial. M usually stands for mass. H is your half-life. length or time usually. So you can see this equation, the only difference here between this one and this one is that your t is negative because we're decaying, we're getting smaller. A is the doubling time, H is the half-life time, like you're either doubling or you're cutting in half. That shows decay or growth. And so the formulas are pretty much the same. So diving into a couple examples here for you. A certain culture of bacteria initially has 25, so here's your initial amount, and it observed to double every 5 hours. And so this is your doubling formula. Find an exponential model for the number of bacteria after t hours. When I'm asking this question, you're going to leave t as t. All right, you're just plugging in everything else. And so we're using our doubling one, and so n of t is equal to n sub 0 times 2 to the t over a. And so we're just going to plug in everything but t. So n of t is equal to our initial amount was 25 times 2 to the t, which is just t over your doubling time, which is 5. And that's for part A, that's all I'm looking for here. I want to make sure you know what to plug your numbers into. Estimate the number of bacteria after 18 hours. And so we're going to use that same formula. 18 over 5 and plug that into your calculator here. Yeah, I would like to see them both at the same time here. You can do that. And so we have 25 times 2 raised to the 18 over 5. Now, some of you need to put your exponents in parentheses because your calculator doesn't automatically bump that up there. Mine does, so I don't. Is about 303.14 nearest tenth, so 0.1 bacteria. After how many hours will the bacteria reach 1 million? And so 1 million needs to go where we have our amount, our actual amount. So we have 1 million equals 25 times 2 to the t over 5 because we're solving for t this time. When you get it like this, we're going to solve it just like we were above. So we need to start by isolating our term with our exponent. So we take 1 million divided by 25 and we get 40,000 equals 2 to the t over 5. Now to get the variable out of the exponent position, I need to convert this to a log. So log base 2 of 40,000 equals t over 5. And then we multiply by 5 each time. So 5 log base 2 of 40,000 is what you're going to type into your calculator from there. And so 5, like I said, I need to go to math for my log base. You're welcome to use the change of base formula. Log base 2 of 40,000. And so 76.439 hours. Okay. All right, and that's, I mean, pretty much it. We can go through these last few examples in class. Well, let me do one more. Let's see here. Hold on. We'll look at this one real quick. The population of a certain species of fish has a relative growth rate of 1.2% per year. It is estimated the population was 2000 was 12 million. Find an exponential model for the population t years after 2000. So we're t years after the year 2000. We're just still leaving t as t. This is exponential growth, but it's not doubling. And so when your population is not doubling, you're using essentially your PERT equation. All right, that's what this is. It's just PERT, exponential growth, not doubling. All right, so it's no different really than the last lesson, those compounded interest formulas. They're just telling you what your P is this time. So our initial population, let's see, we have, 12 million, sorry. We're in the millions, and so we have N of T, the number total is over time is equal to 12. Keep in mind that this is millions, times E to the R as a percentage, so 0.012 times T. All right, so that's your equation. Estimate the fish population in the year 2005. This is where you need to be careful. This is not the time, this is not how many years, this is the current year. And so it's been 5 years since the year 2000. And so what you're doing is plugging in 5 for T. 12 times E to the 0.012 times 5. That's just calculator work from there, which is why it's important you show me what you've plugged in. So 12 times E to the 0.012 times 5. Make sure both of those are in your exponent position. Is approximately 12.742. This is million. So either put that label or convert it into millions, 12,742,000 for that. Okay. And that's it. We'll do those last two in class if you need an extra example of those word problems. But you're pretty much just plugging into those formulas and solving.